Okay, today also we'll solve some problems. Take a problem. Okay, so the dimensions is 150. It's a 10. It's again 10. It's 200. It's a 200. Okay, so what he asked, determine the plastic modulus, just plastic modulus, and shape factor, and shape factor, and shape factor. If you want to find out the moment of resistance of section, if Fy is 250, find out the moment of resistance also. You can moment of resistance of that section. Can you find out? So just see it. First, what we do, we have to find out the plastic neutral axis. What is that plastic neutral axis? That is the equal area axis. Just to do, where it is equal area axis, where it is, just divide it here. Just divide it. How can you divide it, sir? How can you divide it? Just find out the total area. So first total area is what? 150 into 10. So 10 into 200. So what is that value? That value is 3500 mm square. That is in total area. So that axis compulsory divides the area into two parts. So see the bottom area, flange, that is the web area. This is called web. This is called flange. This is called web. So what is web area? Web area is 2000 mm square. It is not an half. It is a more than half. So maybe the axis is somewhere here. Where it is, we don't know. No? So exactly we see that exactly you have to find out that y. How can you find out y? So 10 into that y should be equal to half of 3500 divided by 2, that is a 1750. That's it. So that's 1750. Y is what? 175. How simple you can find? Y is 175. That's it. This is 175. This is 25. So that is the plastic neutral axis. How simple to find out the plastic neutral axis? Exactly, it divides the off. To find out the elastic neutral axis, you have to find out the CG of the section. Center of gravity. That is also easy. Center of gravity. Okay. That is the plastic neutral axis. You got the idea? So we find out the plastic neutral axis. Okay. So next, plastic moment. See, plastic section modulus. Plastic section modulus. Sir, what is plastic section modulus? It is ZP. In M, plastic moment Fy into ZP. That ZP is plastic section modulus. Can you find out the plastic section modulus? Yesterday we did so. So again I will draw diagram. No need to again. It is a 175. It's a 25. Okay. It is a 150. Okay. It's a 10. That's it. That's it. So how to find out the plastic section modulus? So previously I said explain. Previous problem I explained like what is like. So exactly. So every section reaches to Fy. Every section reaches to Fy. So, but one thing I have to remind it. previous day, I said this problem. Where it is this problem? This problem I said sectional C force is 250 into 10. Multiply with directly its distance. I multiply with distance. Now. So this is wrong. So don't follow. Someone did like this. Okay, this is wrong. But answers are right. But they did wrong. So don't listen this problem. Okay. Don't listen this problem. I will give clarify. So today see. So every section reaches to same. Every section reaches to the same Fi. Okay. So diagram is not good. Every section reaches to Fi only. Okay. No problem at all. So if you see what is sectional modulus ZP? ZP is what? M is equal to Fy into ZP. How to find out ZP? This is CRT multiply with lever arm. You already know it. Okay, you already know it. If you see, observe it. So this section reaches to Fy, this section reaches to Fy, every section reaches to Fy. So what is the C force? What is the C force? C force is coming from, this is the C. This section has different area, this section has different area. Are understood? So now it is a C and also this is a C. Are understood? Top section area, if you see, if you take in the top section area, that is 150 into 10, that is Fy. That is one area. And next area is 25 into 10. It's 25 into 10. Both area. This is total area into Fy. What is the lever arm? This is the total compressive force. What is the lever arm? Lever arm you have to find out like, what is the CG of the top area? This CG. What is the CG? This is a rectangle. This is area is different. This area is different. You have to find out the CG of this portion. You have to find out the CG of this portion. Maybe that is CG of portion is in like this. And bottom has this is rectangular. So exactly it's safe. So this area, this distance you have to find out. That is the lever arm. That is the lever arm. Okay. So this area is different. This area is different. So you have to find out this is both combined CG. Bottom has CG. This is bottom has the same cross section. So you have to find out this. Sir, how to find out? It's again hectic process. Just find out it and get it. Otherwise, I will give another suggestion. Not a suggestion. It's easy process. So it's easy. Sir, what is Z, sir? What is Z? Just see what is Z. Z is a I by Y. So what is I? I is mm power 4 by mm. It's mm cube. That is the area into distance. Area into distance. Na? Area into distance. Got the idea? Area into distance. We already know the CG axis. That is neutral axis. Just find out area multiply with distance. That's enough. Sir, for moment of inertia, what you did? If sum of the section is given, how to find out the moment of inertia? Area multiply with, so CG whole square. That's not CG whole square. That is I. What is Z? Area multiply with CG. That's enough. That is the Z. So same thing. See, this is a correct way. To find out the compressive force or tensile force. Both are equal. No need to find out the compressive force, tensile force. Both are equal because we did exactly equal neutral axis. So equal area axis. Top area and bottom area is equal. So area I multiply with y, Fy. So we delete it Fy. So that is no need of Z. So to find out lever arm is difficult because top is a different cross sectional area. So you have to find out again the CG and this CG, that is the lever arm. That means what? this compressive force combinedly act this place. We taken as a combinedly act, but no need at all. I will say simple. So now you can see how to find out this ZP is very simple manner. It is what? It is exactly distance is 175. This is 175. This is 25. This is 200. This is 150. This is 10. So you can see ZP you can easily find out. Sir, how can you, sir? See, top area is what? Top area is what? Top area is what? This is 150 na? See, 150 into 10. 150 into 10. This is where nodal axis is there. The center of gravity of that area is what? This is 5. 5 na? So this is the axis. This is the, for this axis, for this nodal axis, we have to find out the section modulus. So that is what? This is what distance? So this is 10, this is 25, 35. 35 minus 5? 30. This is 30 na? This is 30. This, because this total is 35. This is 25, 10. So 30. So next area, this is, what is that area? 25 into 10, because this width is 10. This center of gravity, where it is located? 25 by 2. What is the 25 by 2? It's a 12.5. 12.5. And bottom area? Bottom area is what? 175 into 10. So what is exactly off distance? Exactly off is 87.5. 87.5. That is a ZP. That is ZP. What is that? 201250 mm cube area into distance. Sir, how? This is ZP. Exactly, this is a ZP. Area into CG distance from that nodal axis. We decide it is a plastic nodal axis. You can easily find out like this. Otherwise, sir, you can check it is like this also. You can check this is the area, multiply with lever arm, delete it F5. Because this is a moment, we only find out it's a ZP. What is lever arm? Just find out it. Sir, how to find out? Just to find out, this is the axis. So this is the area. This is the area. So find out the just nodal axis. Find out the CG. Find out the CG somewhere here or somewhere in the flange also, I don't know. Just to find out on this distance and this distance. This distance is already, you know, it is a 87.5. Just to find out and multiply with, you will get the same. You will get the same. This is the process in RCC steel design. That is the process. There is a normal remembering process. That is a ZP. So you already know what is the moment of inertia. Moment of inertia is area multiply with distance, CG square. Distance square, you can call it as, okay, distance square. So ZP is area multiply with distance. That's enough. You can find it. But reality, the meaning is, the ZP meaning is we decided yesterday class. So, okay, in previous also, you have F is equal to M into Z, you write it. What is Z, sir? Z is I by Y, you write it. This is a just normal process. But in reality, is the compressive force and tensile force, those lever arm, they will maintain. They will maintain like this. Okay, are understood? So that's it. So you got the ZP. So what is Z? Section modulus. What is the section modulus, sir? What is section modulus? Section modulus is I by Y. So what is I? Find out the I. Find out the I. This is the section. This is a 150, 10, it's a 200, it's a 10. Find out the I. To find out I, we have to find out the CG axis. What is the CG? Where it is CG? CG, easily find out. We'll take it from this axis or from this axis, anything. So what is CG? CG from bottom, you can take it as area, 200 into 100. So exactly it's 150, 100. So for this area, exactly at this total distance. 150 into 10, 150 into 10. So exactly distance is 210, 210.205. This is 205. CG, to find out CG, I don't know sir, if you said like this, join elementary school. No problem, okay? So that's it, 205, 205. So divide by 10 into 200, 150 into 10. So what is that value? That value is total 210 minus 65, 145. You will get 145. This is exactly, that is CG axis. 145 from bottom, 145 from bottom. So top is 65, total 210. That is the nodal axis for elastic analysis. This is the CG point, exactly center of gravity of the point. Okay. So if you know the CG, you have to find out the I. So now you can find out I, moment of inertia. So okay, got the idea? So find out the moment of inertia for this area, everything area you can find out. Easily find out, sir. So easily find out. It's 100 into 10, this area. So you have to apply parallax error. Parallax, let's see. Parallax moment, parallel theorem, perpendicular theorem, parallel theorem. You already know it. Perpendicular theorem, parallel theorem. So based on that, you will use I. You will got I as like a 4837750 divided by 3 mm power 4. Sir, now Z, you can find out Z. Z is I by, sir, Y is 145 one, another is 65. Which one is taken? You have to taken Y maximum value. You have to taken, so what is that value? 487500 divided by 3. What is Y maximum? 145. You will get it 1111123563 mm cube. That is Z section modulus. Whereas plastic section modulus is this. Okay, that value 5 point. So now shape factor. What is shape factor? Shape factor is ZP by Z. So that is 201250 divided by 111235.63. What is that value? That value is 1.8. Now we can observe it. Mostly I sections has a shape factor is 1.12 to 1.18. 1.18. But this is a T section. This is a T section. T section has 1.5 to 2. Mostly these range will have. So don't, if you did some calculation mistakes, you get is a 5.6, 6.7. Sir, it's not possible. Mostly is in the range of 1 to 10, 1 to 3, 2.2, 2. That's enough. So got the idea? What is a section modulus? What is a plastic nodal axis? This is the irregular shape. So regular shape, is it easy? Is it easy? It is a irregular shape. That's why I did a one problem. Okay. So previous problem also, if you see the previous problem also, so what you have to do is, directly, no need to write like this, C or T and find out. So otherwise you can easily find out like this. Otherwise what we did now, you can directly write as a Z. Otherwise this is a compressive force, this is a compressive force, both are different areas. You have to find out the CG. You have to find out that those two forces CG and distance, because bottom also same thing, you will get the same value. You have to find out the CG. So what is the mistake? Area is right. What is that area? So this is the area, so the distance is wrong. The distance is something, I think, I don't know. You just find out. You can just find out the CG. Very easy. You can find out. So what is this dimension? This dimension is 100. This is 12.5. This is 18.5. What is the thickness? Thickness is This is 75. So this is 75. This means 75 minus 12.5, 50, 60, 62.5. This is 62.5. The thickness is 18.5. Thickness is what? What I gave? What I gave it? 18 as 12.5. Is it 12.5? Just find out the CG. Just find out the CG. It's very easy. 100 into 12.5. This area. What is the distance? And so remaining is what? 62.5 multiply with 12.5 and CG exactly half divided by total area, you will get CG. That's it now. So that distance exactly, bottom also you will get the same distance, bottom also you will get the same distance, you just multiply with 2. That is the distance. This is not a distance. Okay, this is not a distance, someone did wrong. Okay, got the idea? So you will get the same values are same, he did it, values are the same. Okay, so that is the Z plastic nodal axis and plastic section modulus, general section modulus. For irregular boundary is somewhat difficult. You feel some difficulty, that's why I gave it. Okay, so now I will do one simple problem. Similarity problem. Simple problem. Simple problem. So it's like a section like this. Somewhere they gave it in. It is a section like this. 100, 100, 100, 100 is the thickness is 25. This thickness is also 25. 25. So this is a section look like this. So find out the plastic moment. Find out the plastic moment, MP. So we find out the plastic moment. Sir, just find out the plastic moment. Plastic moment is what? Fy into Zp. So Fy given is 250. Okay, 250. So find out the nodal axis. Plastic nodal axis. Plastic nodal axis is divides the area into half. So if you see, it is a symmetrical axis. It is a symmetrical section. Symmetrical section is both CG and exactly plastic nodal axis are both are equal, because that is exactly this axis is the CG. This point is the CG. Na? This is the point of CG, and also this axis exactly divides the area into half. So both are equal. Okay, no need to find out the CG. So that's it. So now you can find out Zp. Sir, Zp, how can you find out, sir? So previously I said you have to find out this area and this nodal axis and this area, small this portion, this CG, both combined CG. You will do like this. Otherwise, previously I said I by y like this. So you can easily find out by area into distance. Sir, how can you, sir? See, this area is what? This area is what? This area is 12.5. 12.5. It's a 25. Sorry. It's a 25. It's a 25. Thickness is 25. Height is exactly. See, we will decide this area, this small area into second part, because this is has CG is different. So up to this what? It is a 12.5. So 100. This is a 100 exactly. 100 minus 12.5. What is that? This is half 12.5. Na? It is a 25. It's half 25. So 100 minus 12.5. 100 minus 12.5. What is that value? What is that value? So 87.5. So 27 into 87.5, that is the area. This area. Are you got it? This is 87.5, no? 87.5. So what is that CG? So the CG is 87.5 divided by 2. 87.5 divided by 2. This is, but we have to find out this also. Are understood? From this axis. From this is the axis. So plus 12.5. That is the distance. Plus next this area. Next this area is what? 12.5 into a higher distance is 200 and distance is CG is off is 12.5 by 2, half is 12.5 by 2. So that is the top. From bottom you will get same thing, multiply with 2. Bottom you will get the same thing. Are understood? Bottom you will get the same thing, it's off. That's it, area into CG. So what you will get? You will get the value is 2.773 into 10 power 5 mm cube. That's it. And also if you want to find out the shape factor, what is Z? Zp by Z. What is Z? Z is I by Y. Y is common. You have to find out I. Can you find out I? So check it is, find out the I. I value is 1.689 into 10 power 7 mm power 4. Y is exactly, you already know it. What is Y? Y is exactly of 100. This is 100. You will get Z is 1.689 10 power 5 mm cube. So how to find out I? That is a first year class. Okay. So that's it. So what is shape factor? If you see, the shape factor is 1.64. So what is MP? MP is Fy into Zp. Fy is Zp. What is MP? Fy is 250. Zp is 2.773 into 10 power 5. That value is 69.325 kilonewton meter. See, kilonewton meter. That's it. That is the plastic section. Otherwise, if you want the moment carrying capacity by the elastic analysis, Fy into Z. Got the idea? So MP divided by M. You will get Fy is a section modulus. Zp divided by Z. MP divided by M, you will get section modulus ratio. Are understood? So that's it. That is the idea. Okay, got? So that's it. So now we will enter to the another topic. That is a plastic hinge. Okay, plastic hinge. Just I will give you a small idea. I said the section is reaching every point or every fiber reaches to the Fy. Every fiber reaches to the Fy. So strain, if you see the strains, it is greater than the elastic strain. So I already, if you want to draw, I want to draw. This is yield strain. This is a yield strain. The last fiber is almost crosses the Ey. It reaches somewhere. The strains at this point also, the last fiber also reaches to Fy. So this fiber also reaches to this strain. But I didn't show in a strain diagram. So those are irregular. Okay. So that's it. If you see, every fiber reaches to the Fy. This is Fy. Every fiber reaches to the Fy. So once the fiber reaches to the Fy, or the point reaches to the Fy, later that point there is no increment of the stress, but the strain is automatically increasing. Sir, now how to increase automatically? Not automatically. If very small load is applied, the strain is automatically increasing. Strain is very abruptly increasing. That is the point. That is the point. So it is idealized. Don't confuse. It is idealized. In reality, very small. So some irregularities are there. So in reality, it will go. But if you see in this also, very small increment, very small increment. No? Very small increment of force, the strain will increase. So that is, see, one thing you can see. Very small increment of force, the strain is increasing. That means what? It is a plastic material. It's like a plastic. Are understood? It's very small plastic. Some rubber. So take a rubber or some maida. Maida you take in very small force. It's automatically if it just stretches the maida and just to hold it, it gives so many deflections. Na? That means there is no increase of force, but it's a very small force. It will decrease it. It will the strains are increasing. So when the situation is reaching, when the situation is reaching, every fiber reaching to the Fy, the total section is strains are abruptly increasing, very small increment of force. That means what will happen? It's like a that point like a see the section is like if it is a some uniformly distributed something point. This is the point I think. This is the point I think. This point every fiber, the top fiber, if you see the top fiber, bottom fiber, every fiber reaches to the Fy. Very small force it increases to the strains. And also I said the plastic that what is that, the curvature is reaches to pi by 2. The curvature is reaches to pi by 2. If you small applied a force on anything, what will happen? It is strains are increasing. The see just to the point, just to this the point. The point is like what it's like is if you see any aluminum small rod, if you take in, if you did so many multiple times to bend it, what will happen? It is very small weak link. So how it is turning as a, it is turning as a hinge. It's turning as a hinge. There is no strength here. Once if you reach the every fiber like this, what will happen? It is like a just a weak link. There is no strength at that point because every fiber is giving so high strains. That means there is no strength here. There is no strength at that point. Just it's a connector. So there is no strength at that point. That means what? That is a hinge. Understood? That is a hinge. Got the idea? So what is the hinge doing? What is hinge doing? If you just apply it here, what will happen? Then turn, convert it. There is no strength. It is unstable. We already know it is unstable. So the whole body, rigid body's movement is there. There is no this structure. There is no point to taking any load. If you apply a small load, small, just to put it in your finger, it will bend it like bend it because it's a hinge. Are understood? It is a hinge. You know what is the purpose of hinge? What is the doing hinge? Hinge will give any time of deflections. It will give like this also. So once it reaches to this stage, it convert to a hinge. In convert to a hinge, the point is like rotating. So it's I think you already seen the aluminum. If it rotated so many times, if you adjust it, it's bend it. The point reaches to the situation is a hinge. That is called a plastic hinge. Okay, are understood? That is called plastic hinge. But don't confuse it. In general, normal hinge there is no capacity. But plastic hinge has a capacity of MP. Hinge is a moment, na? So plastic hinge has a capacity of MP. Once the point reaches to the MP, it behaves as a hinge. Are understood? It's not a first time. It's not a hinge. The point when the point gets the load of MP, or when the point gives or resist up to MP, later it will convert into hinge. Okay, are understood? So every planet is like a planet. So certain years it convert into a black hole. Are understood? It converts, the solar system is converted into a black hole. Like this, the system, every point has same thing. The point is giving the strength to or resist the strength up to MP. Up to MP it give at the time of MP the strength, all the strength it has, it's already given. So later there is no strength, it behaves as a hinge. Got the idea? That is called a plastic hinge. That is called a plastic hinge. At that situation, this is called unstable structure. You already know it. If you see, it is a structure. If it is structure, it is stable. It takes load. So if you apply a load here like this, if you apply a load here, so it will goes to this, it will give a moment. So mostly highest moment will have a chance here only na? So take that section. If you take that section, it is giving moment of resistance. First it will give m. M is means F into Z. It will give. But you again increase the load. Again increase the load. So it will give elastoplastic. It will enter to the elastoplastic zone. Top fibers starting to every fiber starting to Fi. It giving. So you again increase the load. If you again increase the load, again increase the load up to all fibers reaches the Fi. So that means at that location, what is the moment? MP, if you give in the MP moment at that location, the section gives the MP moment return, resist up to at that point it resists. If you're giving the MP moment, the strength it losses, the stability it losses. This point is behaves as a hinge. Hinge means what? Hinge means suddenly it will give like this. It will give. It's a hinge. If it is a hinge, it will go like this. There is no further loading. Just to put your with the hanger, just with finger, it goes like this. It is unstable. Na? It is unstable. If it is, you already know it. If it is already know it. If it is a hinge is there inside, it's unstable because there is no load carrying capacity of that section. There is no load carrying capacity. It is a hinge. It will cut turn. Just its weak link. There is no. So otherwise, if it is not a hinge, if it is load applied, it will go like this, that's it. Na? If it is a hinge, it gives the rigid body movement, abrupt deflections. So that is called a plastic hinge. This is called a plastic hinge. Plastic hinge has a capacity of MP. Once it reaches the MP, it behaves as a hinge, and the system reaches to a not a stable structure, it goes to be unstable structure. Later it's unstable, and this stage we will call it as a not a equilibrium. It's equilibrium only, but the situation is called mechanism. It's a mechanics. Just it's a mechanism. The situation is called mechanism. Okay. So now if you see, just observe it. For a simply supported beam, for a simply supported beam, it is a stable structure. When it is reaching to unstable, one hinge is required. If one hinge is required, it is going to be unstable. Are understood? It is a stable structure and it is a determinate structure. You already know it is a determinate structure. If you another hinge is there, it is a determinate, na? So exactly it 1, 2, 3. 3 minus 3 is 0. Determinate structure. If one hinge is there, it's going to be 3. 0 minus 1, minus 1. It's a minus, na? It's a another equation will come. It's a hinge moment is 0 at this location. It's going to be another release point. Minus 1. It's a unstable. We discussed the first class of structure analysis. So for this structure, you required one internal hinge. It's going to be unstable, or it reaches to the mechanism. That's it, na? That's it. It requires one. It reaches to the unstable, and it's a mechanism. It's called a mechanism. For a simple, I will give this. Don't take horizontal loads, only vertical loads. So what is the indeterminacy? Indeterminacy, you already know it. It's a movement. Don't consider what horizontal load, just vertical loads take it. So it's required 4 minus 2, it's a 2. 2. 2 is the indeterminacy. Okay, 2 is the indeterminacy. So directly goes to, we will go to the 1. We will go to the 1. So what is the 1? What is the 1? What is the 1? Proper cantilever. Proper cantilever is 1. That's it. So it has, see, it has what? It has the indeterminacy of 1. Are understood? It has the indeterminacy of 1. You already know it. Now you can see it. Now you can observe it. Now you can observe it. The maximum load is here. The maximum load is here. If you applied any load, the load is reaching to this position is higher. Higher, na? It will reach us to MP. So when it is reaching to MP, when it is reaching to the MP, this point is converted to hinge. This is not a hinge. See, first it is a fixed support. When you apply the load, yet that location, the moment applied is reaching to MP, it resists the MP load. But if we already giving it at the time it gives the MP load to the return, it converts to a hinge. So now it is hinge. Now it is a hinge. But you see, the system is stable or unstable? The system is stable, yeah. How, sir? If it is hinge also, it is a hinge also, the system is stable. If it is hinge also, the system is stable. There is no unstable stage. There is no mechanism. So, one plastic hinge is not sufficient to convert into a mechanism. Sir, how many is that required, sir? So, for the one, it will reach to this position. For this position to unstable, we required another hinge. If any another point, any hinge is there, now it converts to a mechanism or unstable. Now we can understand. If any structure is reaching to the mechanism, it requires at least how many plastic hinges? So this structure has required 2. One is here, one is somewhere here. It reaches to the mechanism. But what is the indeterminacy here? The indeterminacy is 1. That's why indeterminacy is 1. So that's why one hinge is happen. That is also, there is no chance to the failure, or there is no chance to unstable. So again extra one requires, it's going to unstable. So for this, it is exactly stable. There is no redundancy. Redundancy is 0. Indeterminacy is 0. It requires 1. Indeterminacy is 1. It requires 2. So now if you see the fixed beam, beams. So I applied a central load. So first, maybe not a first, because if you applied a central load, the bending moment is what? Bending moment is exactly, you already know it. Exactly, it will go like this. This point and this point has same bending moment. WL by 4, I think. Okay, WL by 4 or 8. It's a WL by 8. You already know it. So which point reaches to first the plastic hinge? Which point first reaches the plastic hinge? Which had maximum moment. So which one got the maximum moment? Sir, this point both got the same value. So both reaches to the same situation, same load. Both got the same. Both at a time reaches to the plastic hinge stage. So now you can observe it. This point reaches to the plastic hinge. This point also reaches to the plastic hinge. Both are hinges. If it is both are hinges, so it is going to be unstable? No, yeah. If both are hinges also, it is a stable structure. Again, third hinge happened here, center. Again, third hinge happened at center, because the later it is the point to get the maximum load. Later it is the maximum point. That is the point to get the maximum load. No? So third hinge happened. Then it's converted into mechanism, unstable. So it is unstable. indeterminacy is 2, we required 3 hinges, 3 plastic hinges to convert you into a stable system to a unstable system or mechanism. Got the idea? So that's it. You can now decide that if any structure reaching to unstable or mechanism situation, for that we required degree of indeterminacy or redundant degree of indeterminacy, static indeterminacy plus 1 plastic hinges. That's it. That's the idea. If any structure reaching to the unstable or mechanism situation, for that we require ds plus 1 plastic hinges. Then only it reaches to the unstable and mechanism. So you already know what is unstable, why it is unstable, rigid body movement. There is no talking, so there is no load taking capacity. Okay, so you already know it. Okay, so this is going to be ds plus 1 plastic hinges are required. Those plastic hinges are where it is formed, where the maximum moment is getting, that place the first plastic hinge is formed. The later where the moment is getting, so at that location the plastic hinge is formed. So that like that, it's the plastic hinges are formed. At reaching at final stage, it is unstable, it's going to be collapse. That is ultimate moment of that structure. So if it is a plastic hinge is formed at this location, there is no problem for the structure. Problem is structure is still taking the load. It is a stable structure. Again, if it is a form at the certain where location is a plastic hinge is formed, then only the structure is collapsed. That is called, it's a collapse system or ultimate load carrying capacity. Ultimate final. It's like a collapse. At that situation, it's a collapse, not a recommendations or something. It's like collapse situations. Okay, got the idea? So that again next we will see. Next time we will see how can find out the moment carrying capacity of the structures. Not a sections. These are the sections now. These are the sections. The section has a capacity of MP. You already know what is the MP. We write it. Shear force. We write it. This is MP. The section capacity. Total structure capacity we will decide. Total structure capacity, not a section capacity. Total structure capacity we will find it. The next classes. Before that, some hinge length also there. One topic. Okay. That's enough. Today's is enough.